Welcome back, statisticians. We are beginning chapter 6. You're going to finally find out what normal is. Now, you may think that you're not normal, but unfortunately you are normal. We're all normal in some way. So what we're going to be talking about today is the normal curve. This is like the creme de la creme of statistics. It is the Super Bowl of statistics. If you remember nothing from this course, this is what you want to remember. And we're going to be identifying distributions as symmetric or skewed, the properties of a normal distribution, and finding the area under the standard normal distribution, given z-values. So does this hat make me look normal? That's just a kind of a cartoon. I had a cartoon of a normal curve walking into the bar and everybody yelling norm, but I can't find it to put in your PowerPoint. So it is normal. When you go into the doctor and you have a weird looking wart and they go, is it, and you ask him, hey doc, is this normal for this to look like this? He can look at it and measure it to see if it's normal and if it's within the normal scheme of things and if you have to worry. When they look at your tonsils, when they do blood work, they come up with norms. Is this normal? I can think of the medical industry as a direct application of what's normal. When you talk about grading on the curve, some teachers say grade on the curve. They use the normal curve instead of having it so that most people, you know, it helps everybody. It doesn't help, it helps some, it doesn't help others. So you got to be careful when a teacher says, I'm going to grade on the curve. So when I look here, you know that you have positively skewed and negatively skewed things, and that the bell-shaped, this is where we're going to get our normal distribution. So positively skewed, it means the tail is to the right. Negatively skewed, the tail of the data is to the left. And this is a distribution. These are distributions of that. Now, when we would draw a curve through this, you get the bell-shaped curve. So here's a normal distribution. There's the bell-shaped curve, and this goes down here, that's paranormal, something totally different than normal distribution. So continuous variables that have bell-shaped distributions are considered normal. If we would take the heights of everybody in class, we would have a normal distribution. A lot of teachers will try to make courses so that the people in their course, when they do the grades, they get a normal distribution. Now, the mean can be higher or lower, but if they're reaching what they're supposed to be reaching, most grade distribution should look like this because it's a natural variable. Where did it come from? Now, this isn't on your sheet. By the way, I have pre-printed notes for you, but you shouldn't be writing anything down yet. We're just doing some background information. So the normal curve comes from this. Now, I have to go through this because I am a calculus teacher as well. And if I look at random sample of 100 women and look at their heights, this gives you a distribution. If I make the class width smaller, you see how these rectangles get smaller? If the sample size increases and I do the smaller widths on the classes, I get smaller rectangles. So if I do that again, you can see how it approaches that normal distribution. And if I keep making those rectangles smaller and smaller, that's where this distribution came from. And it's a calculus concept. You don't need to know calculus for statistics right now, but this is kind of one of those calculus ideas as you decrease the rectangles. And we are going to be concerned with the area under this curve, but it's easy. You guys can get this. So here's what the normal curve looks like. So begin the notes. So we have the negative direction. The majority of the data falls to the right of the mean. The mean is smaller than the median and the mode. That's called negatively skewed, and I believe it's left skewed. The normal curve represents a symmetric distribution where your median, your mode, and your mean are all equal. It's continuous and it has a bell shape. It's also how you used to draw a mountain when you were a kid. Majority of the data falling to the left of the mean, that means the mean is bigger than the median and the mode. That is positively skewed or skewed to the right. The tail of the curve indicates the direction of the skewness. So right is positive, left is negative. We're going to be focusing on continuous random variables and normal distribution. Mean goes right down the center value, and they actually have a formula for this. You don't have to do anything with the formula, but I just want for fun, you don't need to write this down, show you what it would look like if you put it in the calculator. So just for fun, let's put it in our graphing calculator and see what happens. We're going to assume we're looking at IQ scores. If you look at IQs, the average IQ is set to be 100. Standard deviation is normally 15. So when we set this up, we just have to plug those into that formula. And it looks kind of complicated, but you need to realize that natural E is just a constant, like pi is a constant. So we're going to plug in this to our graphing calculator into the y equals, and the mean is 100 and the standard deviation is 15. So there's our formula. Here's what it would look like on your graphing calculator. And when you set up the window's kind of tricky. Because I want the median, the mean in the middle, I set the window for x min to be 50 and x max to be 150. Those are my data values. Those go along the x-axis. I set the y scale to be 15. That's the standard deviation. This is a very low curve, so y min is 0.001, y max 0.05, and y scale is 0.01, or 1/100th. When I look at that, bada boom, isn't that cool? I just wanted to do that because I thought that was so cool that, boom, you've got it plotted there. If you're a calculus nut, you could take the antiderivative of this to find out that the area under that curve is 1, but you might not be a calculus nut. So looking on, we're going to section 6.2. That was just basics of section 6.1 to show you where the normal curve comes from. And now we're going to go into 6.2 and the properties of that wonderful, beautiful curve. So the shape and position of a normal distribution curve depends on the mean and the standard deviation. See how it affects the curve in the following figures. So here's a small standard deviation. See how it gets real tall, it stretches upward? The standard deviation is very little down here. Large standard deviation, it spreads it out. So note, the larger standard deviation, the more dispersed or spread out the distribution is. And here's some examples of graphs of normal curves with different means and different standard deviations. So if you want to pause this, you might want to pause this. A and B have the same means but different standard deviations. So if you look at A and B, the means are the same. So they both have the same mean, but the standard deviations are different. B would have a smaller standard deviation and A would have a larger standard deviation. If I look at the graphs A and C, so this black curve and the green curve here, I don't know if you can see the colors on your video, but A is this first curve and C is the second one. You can see that they are identically shaped. You could put one on top of the other. That means the standard deviations are the same, but the mean is different. So that mean for curve A is here and the mean for curve C is here. The last one, if I look, B and C are totally different. So B has a different standard deviation and mean than C does. So both the mean and the standard deviations differ. So it has some cool properties, which is how people determine if your medical condition is normal. And even cars, when they look at the output. Like when you get your car inspected for emissions. Oh, you know you love to get your car inspected for emissions. You know you love that. That's how they do. They look at what should be the normal. They determine what's normal for your car to emit in carbon dioxide. So let's look at the theoretical normal distribution. The graph is bell-shaped. We know that. The mean equals the median equals the mode, and they lie in the center of the distribution. Its curve is unimodal. Bimodal, you'd have two humps. The curve is symmetric about the mean, which means the mean is the axis of symmetry. All right, it divides it exactly in half, and that'll come into play later because we'll get to the areas under the curve and so on. The curve is continuous, no gaps, no holes. It is not holy. Curve never touches the x-axis. It just gets closer and closer without touching. You mathletes out there know that means asymptote, horizontal asymptote. Woohoo! Total area under the curve is 100%. This is a very, 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 very important because the area is going to signify our probability that we get to later. And lastly, the area under the curve within one standard deviation is 0.68 or 68%. Two standard deviations is 0.95. So that means 95% of the data falls within two standard deviations of the mean. If you're within 3 standard deviations, you're within 99.7%. 99.7% of the data. So 99.7% of the data would fall between standard deviations. They say the plus or minus because they're going to go on either side of the curve. So you're going on either side of the curve that, like -3, +3 standard deviations. The area between that, or also the probability, is 99.7. Area and probability, because the total area under the curve is equal to 1. How much is it equal to? 1. Got to remember that. The total area is 1. There is a correspondence between area and probability. I want you to think of them like together when they do this. It's kind of cool. So let's look at this one. I wanted you to copy this down in your notes. Here's our mean right down the middle. Between the area between -1 standard deviation and 1 standard deviation, which means I take the mean plus the little fishy, the little standard deviation, and the mean minus the standard deviation. Notice I have 0 as my mean here. We'll get to that later, but this is actually a standard normal distribution, and we'll get to that. But if I had a mean, like for example, the example I did with the IQs, this would be 100, this would be 115, and this m minus the standard deviation would be 85. So that's how that plays out when you're dealing with actual data. 68% of your data is between there. Here's the exact percentages for each part. For each, can you say it with me, trapezoid looking thing? And then between 2 standard deviations, 95% of the data is present. Notice this little portion here is 13.5. This little portion here is 13.5. And the little tails, 2.28 on each side. To get the z-scores, now the z-scores, the z is the number of standard deviation. This is your formula, which we will get to. So to determine how many standard deviations you are away from the mean, that's the z-score. So once you have this copied, that's all I have for you to do today. We will get to how to change your regular data into a standard normal distribution tomorrow. See you later.